Welcome back. We're still doing test corrections for your midterm, and this video is going to cover questions 6 through 10, starting with question number 6. So question number 6 was one of the most missed questions, which is really disappointing because it's actually pretty easy. Let's talk about how to solve it. It starts with the reading, and I know a lot of people look at the answer choices and just want to jump in, which is fine because you're ambitious, but in this case, if you really read carefully, it would have been a lot less confusing, I think. So it says let f be the function defined by, and then it gives us this normal looking function. It says which of the following is an equation of the line tangent to the graph of f at the point where x equals -1. So in green here, I've just free associated a little bit. When I talk about a tangent line, I know that the slope of the tangent line is the same thing as the derivative at that point. What point? Well, at the x equals -1 point. Now, in order to talk about the point, we have the x value, but I also know that I need to find the y value so that I can use the full point eventually in point slope form, which happened down here. So usually actually the y value is the easiest thing to find. You take the -1 and you just plug it into the normal function. And when I did that, I got the math done out right here and I got an answer of 4, and that's the y value of the point. So we're talking about a line that goes through the point -1, 4. Now the slope of that line is the same thing as the derivative at -1. So first thing, I took the derivative of the original function, which is just power rule. Multiply times 3, subtract 1. Drop the x here because we basically multiply times 1 and turn it to a 0. The 3 disappears and we get 12x squared minus 5. Then I plug in -1 for x, and I get 7 is the slope of the function at -1. Then I just plug into the point slope equation. It's y minus y1 equals mx minus x1, and the minus turns to a positive. And from there, we just have to convert into slope-intercept form, which you won't always have to do. These answer choices maybe sometimes will be in point slope form. It's just a little bit of algebra. I distribute the 7, and then I add 4 to both sides. Not so hard. All right, you try one now. Right, so the answer was C, and here are the steps. First, I found the y value, and I did that by plugging in 2 to the original equation, and the y value was -3. Then I found the slope, which meant first taking the derivative of the equation and then plugging in 2. I got a slope of 3. I used point slope form. y1 is right there, the slope, and then x1. And then I just converted back to intercept form. Question 7 didn't seem too hard for most people. Basically, you just have to remember that the definition of a limit existing is when the right-hand limit equals the left-hand limit, which means that the two sides of the function have to come together at that x value, whatever the x value we're talking about. But at the exact point, it doesn't necessarily matter whether the actual point is on the line or separate from the line or undefined, whatever that. Really, it just matters that the two sides come together. Remember that continuous is the definition where all three have to be the same, but the limit exists as long as just the two sides equal each other. So in this case, the y values when I approach 4 from the left, and when I approach 4 from the right, the y values are approaching each other right here. In this case as well, for 2, the y values of the pen as I approach x equals 4 on either side, the y values are approaching the same number. In this case, it looks like it's 4 or something. For the last one, the y values don't approach the same number. When I come from the left and I go towards 4, or when I come from the right and go towards 4, in one case, my y values are up here at 4. In the other case, my y values are down here at 2. It's a jump discontinuity. The limit does not exist here. Try this one for you. Here you go. Yep, this should be pretty simple. The answer is E, and that's just because at x equals 4, the right hand and the left hand limits are the same for 1 and 3. If you want to see that, think about tracing them and pay attention to where 4 is, because this is trying to trick you here. 4 is right here. If I come from the left towards 4 or from the right towards 4, my y values on both sides are touching the same point. Here they're not, because there's a jump discontinuity at 4. And here, if you were careful, 1, 2, 3, 4 is actually right here, which is just a normal point. From the left, from the right, we're approaching the same. Obviously, there are holes in other places, but at 4, the limit exists. In fact, it's also continuous. Question number 8 was a little disappointing. A lot of people have forgotten this graph stuff, so let me just jog your memory. In the original function, anytime the original function has a horizontal tangent has a slope of 0, which means the derivative has to be 0 at this x value and this x value. So that should be your starting point. Basically, you're looking for a derivative function that has 2 intercepts. When you look at the graphs, you can see that 2 intercepts is probably going to be a parabola. This has 2 intercepts, this has 2 intercepts, this one doesn't, so rule out C. This has 2 intercepts, this one has no intercepts, so rule out E. If we're now deciding between A and B and D, you want to look at where the intercepts are and whether or not the y values of the derivative should be positive or negative. Right here, the beginning part of the graph, all the way up to like, I don't know, maybe -1, the derivative should be a positive number because the slope of the original function is positive. So in A, we start out with positive slopes. Not positive slopes, these are y values. The derivative values are positive because the slope in the original function is positive. That's good news. Right here as well, we start out with positive y values because the slope at the beginning is positive. Down here, we start out with negative y values. If the y values of the derivative function are negative, the original function should have negative slope, but it doesn't, so I'm ruling out D. Now, to compare A and B, it's really just the placement. Notice where the intercepts are in B. They match where the vertices are in the original function, and that's why B is correct and A is incorrect. Here's one for you to try. Great, here's one for you. Okay, hopefully that went a little bit more smoothly. The answer was B. If you think about what the original graph looked like, it had 2 vertices. So I would expect my derivative graph to have 2 x-intercepts, one slightly on the negative side and one slightly on the positive side. Oh, I'm sorry, there are 3 of them, and then 2 slightly on the positive side. There's 1, 2, 3, which is why both answer choices B and E seemed to have the right kind of intercepts, 1 on the left and then 2 intercepts on the right. Now the difference between the 2 is that this one starts above the x-axis and this one starts below the x-axis. So if I come back to my original graph, the actual function starts out with a positive slope, then has a negative slope, then has a positive slope, then has a negative slope. So the y values of the derivative should start out positive y values, then they should have negative y values, then they should have positive and then negative, which is why B was the correct answer. So you probably remember that question number 9 was technically a bonus, but it was really only a bonus because of timing, and this is a perfectly fair question that I could ask you on the final. So let's make sure that you understand why the answer is does not exist. This is a non-calculator section of the test. If you had a calculator, I would just instruct you to put this into y1 and then use the table to look at what happens near x. You don't have a table though, you don't have a calculator. But who's to say we can't do the same thing just kind of using your common sense? Basically, whenever you do a limit, you ask this question. What happens to the output or y value as x gets really close to 1? Well, one way to do this is to think about what it means to approach 1. And always there are 2 ways to do that. You could approach from the left or from the right. So what I did, and maybe on the test I wouldn't even do all this work out, but conceptually, I thought about what it means to get close from the left. If I'm getting closer and closer to 1, and I'm thinking about numbers on the left of a number line, I'm talking about numbers that are smaller than 1, like 0.9, 0.99, 0.999. And then I had to think about what would happen if I plugged these numbers in. Well, when I think about plugging these numbers in, the top of the function is really basically the same thing as e to the 1, which is really just e, and I approximated that as 2. It's a number, right? It's close to 2, it's a little bit more than 2 actually. And it doesn't actually matter if I'm really precise about the top function, because actually the bottom of this fraction is what's really changing the most. And that's because when I plug in numbers really close to 1, and then I subtract 1, I'm going to end up with really small decimals. In fact, with really small negative decimals. And as these decimals on the bottom get really, really, really small, the whole value of the fraction is actually going to get really, really large. And that's because the top is really not changing that dramatically. The difference between 2.7 and 2.8 is nothing compared to the difference between dividing by 0.1 and dividing by 0.0001. Using this kind of logic, we have a number on top, a positive number, divided by a very small negative decimal, a decimal that's getting infinitely small on the bottom. And that means from the left, this function, the y values are approaching negative infinity. I use the same logic on the right. What's going to happen? Well, first of all, what does it mean to be on the right? It means to get closer and closer to 1, but to be a little bit bigger than 1, like 1.1, like 1.01, 1.001. When I plug these numbers in, the top of the fraction is still basically just e to the first power. And yes, these exponents are slightly different, but they're all kind of within the same range. What really causes the problem is on the bottom, when I have numbers very close to 1 that are getting infinitely close to 1, and then I subtract 1 from them, I end up with very small positive decimals, decimals that get infinitely small but stay positive. And when you divide a number on top by an infinitely small decimal, the y values are going to approach positive infinity. Now, the definition of the limit says if they're different, if the limit is different on the right and the left, that's why it doesn't exist. You, again, to reiterate, do not have to do all this work out. You do need to somehow come up with this logic, the logic of, well, what happens here? Basically what happens is on one side I get a small negative decimal, and on the other side I get a small positive decimal, and that's going to cause a discontinuity, an infinite discontinuity. Try this one. Remember, you can't use a calculator here. Okay, so in this one, the answer is going to be A, and I explained it this way. We're approaching from the right, and if you missed that detail, then you probably got it all wrong. That little plus means we're only thinking about the right-hand side. We're no longer thinking about overall. So just thinking about the right-hand side, well, if I approach 2 from the right, the top is going to get close to 8. The bottom's going to turn into a small positive number, which means the answer is going to be positive infinity. If you need to think about the reasoning a little bit longer, go ahead and press pause. Otherwise, we'll move on. All right, question number 10 is where I really have you start working for it. This is basically just another example of our problem-solving seminar. And I've written out each step that I took, so I'm going to scroll through them briefly. Take the time to read through each of my steps and make sure you understand each move that I made. And the best thing you can do is try to explain to yourself why this line of work equals the one before it. Think backwards here. And then once you know why they're the same, then ask yourself the question, okay, why did I want to add a 5 on the top and the bottom here? Or why did I want to rewrite tangent? Think first about why it's right and then about why I would want that. I'm going to save my minute and a half here to explain the example that you're going to do. So take a moment to look at this and see if you can follow each step. And now let's try one for you. All right, the correct answer was D, as you saw in Edpuzzle. And the work's actually not quite as long as the one that you did. Let's look through each of these steps. So my first move was to think of that x squared out in front. My next move was to convert cosecant and tangent to their sine-cosine equivalents. My next step was to flip this long fraction, so I kept the top and flipped the bottom. From here, I start to think strategically. I know that these signs are causing a problem, and I know that one way to solve that problem is to end up with a sine x over x kind of situation. So I'm redistributing here at the next step. I put one of these x's next to this sign, and the other x next to the sign on the bottom, and then I keep the cosines separately. I multiply by 2 here because I have the 2x inside. And then my last step I figure out what I've taken care of. That's taken care of, so is this, and this is what's left over.